Yes.
Okay, so we just started. It's just, so welcome, Gonçalo. He's our second speaker. Thank you for joining us, maybe from Edinburgh or from Lisbon. Where are you?
Na Serra da Estrela.
Okay, in
In the
Portugal.
middle of Portugal.
Okay, so welcome anyway. And thank you for accepting my invitation to participate in this session. Martha, I go back to you. Thank you very much. And finally, our main speaker, Thorsten Smith. He's a co-author of mine as well, and we have actually a joint project on mathematics and insurance, and in mathematics for insurance and finance, and this was the main motivation for creating this session in this important event. Okay, so thank you, Thorsten. I remind now the rules of the game. So each speaker, Manuel, will have 15 minutes, and then we have at least 5 more for questions. Okay, so Manuel, you may start sharing your slides. Okay, and now the stage is yours.
Thank you very much, Raquel, for the invitation. It is a pleasure again to be part of some collective work with you and the other speakers. Some of them I know very, very well. Others I know well, but from reputation. And so it's a pleasure. In order for us to be able to keep on schedule, I will try to go fast, but of course moderately fast. So this is something that was done initially with insurance purposes, but it can be used also in finance, for instance, in credit risk, or we will see how. So this is joint work with Nadezhda Krasi from Rostov-on-Don, and Gracinda Guerreiro, who is our colleague at the Faculty of Science and Technology of the new University of Lisbon. So let me just say how I can do this. Okay, so what we will do, there are 2 main sections. The first one is how it's about how to pass from discrete to continuous time, and then the second section is how to use this tool from passing discrete to continuous time to study open populations. So let me start with an example. So we had a problem with data coming from continued care institutions in Portugal. So it was a big database that had information about people in continued care. It was just one year, 2015, and it had something like 120,000 records. And so what we did was we made an analysis by utilizing clustering tools, and we came out with some transition matrix that we could think of as being the probability transition matrix for the population, jumping, the elements of the population jumping from one state of their continuing care to another. So there was healthy and then 3 intermediate states, and then out of the system. Okay, so we have 5 by 5 matrix. Okay, so we had this matrix, but we needed to know more. We needed to know, or at least to model, the transition times between states. Okay, so if the model is discrete time homogeneous Markov chain with this transition matrix, we don't know the laws of transition times. And so it came the idea that we could try to obtain a continuous time Markov chain that would be in some sense close to the discrete model. And what we did was we considered the powers of the discrete time transition matrix with a generic term given by Pij to the n. So this is the this n is the n-step transition matrix of the discrete time chain. And then we took some model, continuous time model, depending on a parameter. So this was done by using the intensities, and the intensities had parameters. So we defined this loss function, and we look for the parameter theta that would give us a minimum for this loss function. And then we could say that in some sense, the continuous time matrix was close to the discrete time matrix. And then what we did was to simulate trajectories from this continuous time Markov chain. And then with these simulated trajectories, we could obtain things like the distribution of cost of the long-term care, and then also the lifespan from age 65 on in this histogram. And this histogram of the lifespan was compared to the histogram for the true data of the Portuguese population. Okay, so we had a way of comparing that everything was in some sense close to the reality. So this was our main motivation to start the work that I'm now going to present. So the thing is, what can be said? Because when we looked at this optimization problem, we just had to apply brute force to get the continuous time Markov chain depending on this parameter. We have to just perform the optimization and get the best we can. But we didn't know the structure of the thing. So we try to understand this. And the first idea is to consider the concept of embeddable stochastic matrix. So you start with the numerical matrix, and you say that it is embeddable if there are stochastic matrices such that you verify this equation. So this is Chapman-Kolmogorov equation that forces this to be the continuous time transition matrix for continuous time Markov chain. And then this is what gives the link between the continuous time transition matrix and the stochastic matrices that can represent the discrete time model. And so this is a very surprising work and result, I think, from Goodman, and it is really very interesting. The idea is that this time that you get here is simply given by this expression. So you take the determinant of the stochastic matrix, you take the minus log, and then you have this time. So it's really something very surprising, and it has a lot of very interesting consequences, and it is something that has deep algebraic meaning also. But we are not concerned about this. We just need the fact that in some cases you can embed discrete time stochastic matrix in a family of stochastic continuous time stochastic matrices. And so what we did was first try to prove in all generality a result that could give us the possibility of calibrating a continuous matrix by using a discrete sequences of discrete sequence of matrices. So what we have is we have a family of transition matrices taken at an increasing sequence of dates. So these dates are not random. And then here you have the family of intensities. So these intensities are depending on a parameter. Okay, so we build them depending on a parameter in such a way that these two first and second hypotheses are verified for the intensities. But we also have this very, very important hypothesis, which is that you somehow have a control of the minus intensity taken on the same states by a locally integrable function. Okay, so this control is very, very important. It's something that appears, and it is almost essential in whatever we try to do. And I will show, I will tell you where.
5 minutes. 5 minutes.
Okay, so so the result is that then we have this solution of the optimizing problem. Okay, and meaning that for some values of the parameter, this function attains this loss function attains its minimum. So what can we say? We can say that if you have a discrete time chain whose matrix is embeddable, so there is optimal calibration result. So the fact that the matrix is embeddable gives us optimality of the calibration result. Also, we have a weaker result if not this happens, but there is a sequence of powers that are embeddable. So the chains can also, the chains with this property can also be optimally calibrated. So this ends the idea of calibration of continuous time from discrete observed time. Now let me briefly recall what is the open Markov population. So when you have the idea in this graphic is very simple. So you have a population with states, and you have new members entering the population. Usually what happens is that if there are no new members, if there is a closed population, transient states don't matter. But what happens here is that as you have new members entering, the transient states matter. So let me just tell you how it works. So you have discrete time transition probability matrix, okay? And when you have this decomposition between the transitions, K matrix is the transitions between the transient space states. V is the transitions between the non-transient states, and the U is the mixed transitions. So when you consider the power, you have this law. If you have a spectral decomposition of the matrix K, the powers of K are given like this. Eta G are the eigenvalues, and alpha and beta are the eigenvectors. And what you have is that the populations, the subpopulations in the transient states, they together have a vector of mean values, and so as they are Poisson distributed, the vector of Poisson parameters that is given exactly like this with this expression, with t, small t is just the vector of initial classification, the way you distribute the new elements between the states when they enter. So now I'm just going to tell you what happened. How can we connect these two things? So the idea is that we have, as usual, a complete probability space, then a stochastic process, a sequence, continuous time stochastic process, a discrete time stochastic process, and an increasing sequence of random times that do not accumulate. So this hypothesis is essential because if the stopping times accumulate, you cannot see them, you cannot identify them. So this hypothesis is essential. And for this hypothesis, the domination hypothesis over the intensities is crucial. So if you have this domination hypothesis over the intensities, you will have that the stopping times do not accumulate. So process, we say that the process Y has this structural representation with the discrete sequence of random variables, and then the indicator function of the intervals between the stopping times. And if you can write it like this, so you decompose the random change of states by Zn and the time at which it happens using the stopping times. So this structural representation works for homogeneous continuous time Markov chain, for semi-Markov process, and for non-homogeneous continuous time Markov chains with certain hypotheses. So if, for instance, if Zn is a Markov chain and the times between jumps are exponential distributed, what you have is that this representation gives you an homogeneous continuous time Markov chain. And another set of hypotheses give you a semi-Markov process, and another set of hypotheses of over Zn and the stopping times give you non-homogeneous continuous time Markov chain. So what we have is that we can now say what happens with a continuous time process if the influx of new members in the population is Poisson distributed, with the function that gives the parameter of continuous function of time, if the stopping times are finite, and if there is a unique limit at plus infinity whenever you take some subsequence of times going to plus infinity. And the result says that now you have the vector of parameters in the open Markov chain, which is, this vector is a random vector. And what you can say is that the expectation of this random vector converges to something that has exactly the good limit at the infinity. So you continue to have stability at the infinity of the expected values of the vector of the random parameter in continuous time. So
okay.
this is a generalization of the result in discrete time. And this is work that is been taking for a very long time. It started 2010, and some of the publications are here. And this is open Markov models, open population Markov models. It's a very wide subject, and in these references here, you have also an history of the subject. So thank you very much for your attention.
Thank you, Manuel. I know 15 minutes is really short, or then you didn't want to allow for questions.
No,
So
no.
I'm kidding. So please, I also start by thanking the attendees, some of them quite well known as Carlos Brauman and so on. They are seeing, so welcome to this session. So feel free to write on Q&A any question you want to pose to Manuel. And of course, the panelists can also pose each other direct questions because you are voiced if you want. Gonçalo, you can pose the question directly.
No, I only have a question. I have a couple of questions. So you embed the sequence of discretely observed matrices within a structure of a continuous time Markov chain. So do you is there any non-Markovian dependence, or the fact that you recalibrate for this parameter allows you to circumvent this?
That's it.
And then the question is, do you have stability with relation to this parameter that you're estimating? As you move from tau n to tau n plus 1, does the parameter change a lot or just a little bit?
No, it doesn't change. It is taken globally. It is taken globally. What we observed in the numerical experience that we did in the second paper is that the adjustment between the transition probabilities in discrete and continuous time was not very good. You are committing an error or something globally. You are committing an error of something like 10% per each of the discrete transition probabilities. So it's not an adjustment that goes very close. There are differences. So the curves have more or less the same shape, but they are not equal. But nevertheless, it gives good information. So it's we don't understand fully this thing, and so we have a lot of fun working on it.
And that's the purpose of research. I don't think there are more questions, but there is a comment from Professor Carlos Brauman saying, congratulations, very interesting presentation. So thanks for also this comment. And without further ado, because we are a bit behind, 2 minutes behind time, I would ask Gonçalo, you are the second speaker, to share your presentation. And as happened to Manuel, you will have 15 minutes. I will let you know 5 minutes before and 1 minute before end. Okay.
I'll go lightning fast. So you can see my slides?
Perfectly.
Yeah. Okay. So I want to talk about work that I've been doing, a sequence of works that I've been doing with my PhDs regarding simulation of McKean-Vlasov equations, or mean field, or so-called mean field equations. So What you see at the top is a mean field equation. Is just like a standard stochastic differential equation, but has the difficulty that you see the law of the solution process appearing in the coefficients. And so, for instance, a very easy example would be, imagine that you have the expectation of the solution process inside, or some other functional like value at risk that depend on the law of the solution process appearing in your dynamics. So then how does one go about doing simulation for this kind of thing? And in particular, I want to focus on superlinear growth type coefficients that appear. But before going into the specifics, so this mean field equations, they got quite a lot of attention. So mean field equations, they're around since the 60s or the 70s, coming from problems in statistical mechanics, but they've gotten quite a lot of attention over these past 15 years due to their new connections to them being employed in a lot of problems in economics and financial mathematics through mean field games and so on. So they allow to model first order interactions between economic agents. You can take the limit, allowing you to reduce dimensionality and so on, has applications to biology, chemistry, neuroscience, plasma physics, and so on. And in particular, there's even more recent work describing the limits of neural networks, either that have infinite layers or have infinite neurons, as mean field equations and optimal control problems. So there's even one more recent that really got my attention, which is that GANs, a type of machine learning algorithm, can be described as a mean field game, can be equivalently rewritten as a mean field game, and then you can pool theory and tools of analysis for mean field games to understand neural networks, but also use neural network algorithms to understand mean field games. So this is just in a nutshell, the kind of stuff that's going around. So for my talk in particular, I want to talk about how do you numerically approximate stochastic differential equations of mean field type, as you see up here, where the sigma, assume that sigma over here is uniformly Lipschitz in its variables, B will be Lipschitz in the Wasserstein metric with respect to the measure, but will have superlinear growth in the form of the so-called one-sided Lipschitz condition. And so this is the setting that I want to talk about. So first of all is, how do you go about dealing with this expectation term that's in here? So the main trick is you go into you can draw on a Monte Carlo idea, which is to say that an expectation is given by the average of a sequence of samples, which then allows me to rewrite this stochastic differential equation that's here, that is in RD, but as a system in RD to the n of fully coupled stochastic differential equations. And here they're coupled because I've replaced the measure component by its empirical distribution. Or so to say, where I had the term expectation of X, I now have the weighted average, and this goes across all the I particles that I write on my system. Okay, so each of them will get its own independent Brownian motion, and so there's some kind of from line to line, there's this common structure, and this is at this level. This is now a standard ST, but it's, as you can imagine, it's very high dimensional and fully coupled. So there's a classical result called propagation of chaos that basically explains that as you send the n to infinity, this interacting particle system will converge and recover the original equation. And so what we the first thing that we did, this is an asymptotic result, of course, was then to put a convergence rate into the system, basically saying that this being the true solution of the McKean-Vlasov equation, this being one of the particles of the interacting particle system, and then it says that there's a convergence rate of the order of n, the fourth root of n, when you write this in mean square error. Okay, so I go from the mean field equation to the particle system, and I can quantify the convergence rate there. So if I want to do numerics, then what's left for me in this program that I'm describing is how do I numerically approximate this high dimensional system that's now an SDE. So a priori, all kinds of techniques from SDE work. The problem is, or the delicate part is that I need to show that everything is independent of capital N. Otherwise, the numerics will blow up when I pass to the limit for the approximation. So the question is, can we, so we first went to answer, can you make explicit Euler schemes recovering standard convergence rates when you have superlinear growth? And then how about implicit efficient schemes? And efficiency here has a specific meaning. So let's go back to the setup for me to give you an idea. So this is the standard McIntyre equation. And I want to emphasize again, superlinear growth in X, the rest is Lipschitz. This is in RD, and now I write its particle approximation in RDN. So the system is fully coupled due to the presence of this Monte Carlo trick over here. And if I was doing standard numerics, where I would just do, pick up my scheme and do a standard discretization across a time grid, I would put their TK. This would be the Monte Carlo on the TKs, and then discretization of the Brownian motion. And if I would plug this explicit Euler scheme into a computer, in this case with this standard case over here that I want to do, because I have this superlinear growth inside. As I'm doing the simulation, each line over here represents a simulated particle. And there is one particle that at some point will go completely crazy and will destroy the simulation across the whole system, because the system is fully coupled by the expectation appearing here. So note, I'm trying to simulate this up to time 2, and I'm only able to go to time 1/2. So this is the problem you have when you have superlinear growth type equations, or you have sort of explosive potential 1/0 explosion, but that's not the case here. So, and this is what we coined this particle corruption, as one particle gets corrupted and corrupts all the whole system. So you need to come up with smarter ways to deal with superlinear growths and so on. And so what we did, we went to this old literature on numerics for SDEs, and we ended up by finding something from the splitting techniques world. So it's something somewhat inspired by numerics for ODEs for 20 years ago or something, where essentially what we do is we break, in the Euler scheme, I'm solving this equation at each time step. The idea behind splitting is that say again?
5 minutes.
5 minutes. So the idea behind the splitting methods is that I'm going to add in an intermediate step. So I'm going to break my drift into V plus B, where V is the part that contains all the superlinear growth, and that I'm going to solve via an implicit method over here, equation 1. So this should be a TK plus 1. This is a typo. And I solve this, I extract its properties. You can prove from the theoretical point of view that the solution has very nice properties. And then I'm going to plug this into equation 2. So this is a kind of, this is why we call this a split step method. The advantage of doing this is now the system, although it couples through the empirical mean, the system 1 is fully decoupled. So I can imply and I can implement all of this in parallel, and implicit methods will have better stability properties as opposed to explicit ones. So this is why this method ends up by working very, very nice. So we end up by, we make the standard convergence statement saying when do you have, under which conditions you converge. So you see here the n, the 1 over square root of n from the propagation of chaos result, and then the h from the time step discretization by employing the Euler scheme. And so everything here is within its rightful place. So this is another method that I'm going to jump, an alternative to solve implicit methods. And so basically we went to implement this on a computer. We went we grab the 3 standard answers you have for superlinear growth at this time, which is taming, which is a type of dynamic control, so that this it's a type of truncation so that this isn't superlinear. You have time adaptive, which is the time step is not fixed age, but it varies and shrinks depending on the size of the cloud. And then you have the split step method, and all of them will get their convergence rate 1/2, with taming being 1 order higher in magnitude of error. On the left-hand side, so the only thing that I want to point out here is that we then implement this in 4 cores for parallel, and we get a reduction of the running time to 26% of its initial running time. So which says that even though we're using an implicit scheme, we can compete in terms of parallelization and so on with a fully explicit scheme. 26% time with 4 cores is because you always need to have some kind of communication between the steps, so you can never be perfectly parallel. So this is within our main motivation are these models for interactions of clouds of neurons on the brain, and this is just a very ugly model that breaks the brain into a sequence of capital J areas. The neurons interact within each of the areas, and then at some point they will reach a threshold and they will start to influence all the surrounding areas. And this is why the mean field modeling comes into play. So this is just to say that there's a very ugly model motivating all of this. We managed to put everything into the system, get convergence, everything is okay. We can get really nice smooth densities out of the model, and these are essentially the results we have. At present, there are 3 competitive algorithms to simulate McKean-Vlasov equations of this type: taming, time adaptive, split step. They all do convergence rate 1/2. There's still a big open problem, which is I've shown you was superlinear growth in space, but it's unclear how you do superlinear growth in measure component. When it's non-Lipschitz in the measure component, you have superlinear growth there. And there's only 1 result so far on this. And this is something that we're working on. And then because I knew Manuel was going to give a talk, I added this last line, which is, are all these methods fit for purpose? And the answer is no. If you're using them on finite time for finance, mean field games, and so on, it's fine. Now, if you want to do statistics, in particular parameter inference, where likelihoods for these kinds of things are really difficult to write down, it's called untractable likelihoods, and you want to use simulation-based modeling or Bayesian analysis to do parameter inference, then these kinds of methods, these 3 methods, they're not fit for purpose. They don't preserve systems geometry. For instance, they will be phase space will be off the place where it should be. You recover an invariant distribution that's not the right one. And so if you're trying to do parameter inference by knowing that there is an invariant distribution in the end, and you're not capturing it in the right way, this means that you're not going to get the right parameters and so on. So this is also something else that we're working. And this is what I wanted to talk about. So thank you.
Thank you, Gonçalo. I will ask the audience to post questions on Q&A, and if any of the panelists wants to pose a question while we wait for some, yes, Manuel, you can unmute yourself and just pose it.
I was interested in the improvement in execution time due to parallelization.
Yeah.
Because we have just finished a work where we can show that it has to do with the number of cores, of course, but it goes exponentially. So if you have time of execution, so a rate of convergence going to 0 of the original algorithm, when you use parallelization, for instance, with 4 cores, the speed to 0, the rate of convergence to 0 is the speed of the original algorithm to the fourth power, more or less. So I wanted to understand better what you have recovered as a result of parallelization.
So the 3 lines, the top 3 lines, are just implementing the algorithms on a single core and let them run. We measure the time. And then the bottom 3 lines is we went back to each of the algorithms and we split the 4 loops, so to say, by the 4 cores. So as you can, so let me see. So in standard, if I was doing standard Euler, and this would be a decoupled system, and if this would be 10,000 particles, I would put 2,500 in each core, and the method would be perfectly parallel. Because I have this interacting particle system, it means that every time I give a time step, all the cores need to come back and need to join the information. So this is the point where you lose parallelization power.
Okay.
So when I'm doing my split step method, I have the advantage that I can perfectly split the task of equation 1 because it's fully decoupled. So there it's 100%. I get the right reduction in parallelization power. Then after the first step, then it needs to compute this empirical distribution, split, give it to equation 2, and once it's fixed, then I can split equation 2 back into the 4 cores. So because at every time step I need to do this, the cores have to stop. They need to recalculate this point and then come back. Now imagine that in general, you'd be putting on different cores, different parts of the more complex algorithm. If a core gets sorted out, does its calculations sooner, it will have to wait until all the other cores and so on. So this is a well-known problem in terms of reducing parallelization computing time. Yeah, exactly.
Okay, thank you both. I see no further questions, so I will ask Gonçalo to stop sharing the screen and Marta to set up, get ready. And in the meanwhile, I go back to the attendees that are quite silent in this meeting because they don't have voice or camera. And it's always a pleasure to see our descendants, so students that we have supervised, to show up in meetings. So Rita, welcome, Rita Pimentel. And it's also nice to be accompanied by a colleague from ISEG, Manuel Guerra. And I apologize, I cannot mention all the attendees by name, but it's good to see that you are steady. So you are there and you are staying with us in this meeting on mathematics for insurance and finance. And now Marta is ready, as far as I can see. So Marta, the stage is yours.
Thank you, Raquel. And let me start by saying thank you very much for inviting me to this session. It's a pleasure to be here and to present my work, which is perhaps a little bit different from the works that we have seen previously, but I hope it is interesting anyway. So I'm going to talk about credit market segmentation, essentiality of commodities, and supermodularity. So actually, this work is about existence of equilibrium in an economy with financial markets, where agents are subject to restrictions. So that is, there are trading constraints. So actually, segmentation here means that there are agents that are not allowed to trade all the assets in the economy. When we have this hypothesis or this setting, there is some problems to prove the existence of equilibrium for these economies. Actually, the standard assumptions are not enough to prove existence of equilibrium. So what we actually have done in this work is to add some assumptions that will solve that problem that allows us to prove existence of equilibrium in these models. And that assumptions are actually essentiality of commodities and supermodularity. So I'm going to start describing the base model, and then I will try to show you what are the difficulties and how we solve them, and this way how we contribute to this literature. Okay, so let me start describing the base model. We consider an economy with two dates, date 0 and date 1, with uncertainty in the second period or at date 1. So this is more or less the scheme for our temporal and uncertainty structure of our model. So there is a finite set of commodities, held commodities in each state of nature of at date 0 and at each state of nature of date 1. We consider an economy with a finite set of agents or traders or consumers, as you prefer. These agents are characterized by an utility function that is defined on the consumption set and an initial endowment of physical commodities. We also consider in this economy a financial structure. So we have J financial products or assets that are traded in the first period, and then they pay returns at date 1, in the second period. Okay, so a consumption bundle or a consumption plan in this economy is a consumption bundle of physical commodities and a portfolio. So this is the notation for the consumption bundle of physical commodities. So we have a bundle for date 0 and a bundle for each state of nature of the second period. This is the portfolio of assets, and if Z is positive, this means that agents are purchasing or doing an investment. If Z is negative, this means that agents are short selling or making a credit. Okay, the financial structure in this model is given or described by these metrics. So in each column refers to the returns of an asset. So this column J describes the returns of asset J in each state of nature of the second period. And if an agent trades this portfolio, then the returns of this portfolio in the state of nature S are given by the sum of the returns of each asset. Okay, so this is our economy, which is characterized by a payoff structure, physical commodities, and agents that are characterized by utility functions and initial endowments. Okay, so the problem of a consumer in this economy is to choose a consumption plan, that is a bundle of commodities in the portfolio that maximizes its utility and are subject to the budget constraints. Okay, that is, the consumption plan has to belong to this set B, which is the budget set. So, and the budget set is described by these in equations. So we have a budget constraint at date 0 and the budget constraint at date 1 for each state of nature. Let me just read what is the budget set at date 0. So at date 0, agents choose a plan of consumption. So the value of that bundle of commodities plus the value of the portfolio has to be less or equal than the value of his initial endowment. And in the second period, at each state of nature, the value of the bundle that they consume has to be less or equal than the value of the initial endowment plus the returns of the portfolio that he has transacted in the previous period. Okay, so this is our economy, and the competitive equilibrium for this economy will be a vector of prices for commodities and prices for assets, and a consumption bundle or consumption plan for each agent, such that the consumption plan for the consumer has to maximize its utility under the budget constraint for these equilibrium prices, P bar, Q bar, and then there is market clearing in the commodity market at date 0 and at each state of nature of date 1, and there is also market clearing for assets. So this is the equilibrium. And then under the standard assumptions, we can guarantee that this economy has an equilibrium, as a competitive equilibrium. Okay, let me just describe very succinctly how we can get the existence of equilibrium to show you where we have difficulties when we consider that the agents are subject to trading constraints. Okay, so to prove the equilibrium, what we usually do is to consider a correspondence. So a correspondence is a function such that the image of an element is a subset of the codomain. So we consider a correspondence, define it in a compact set, which is in this case a subset of the set of prices and a compact subset of the set of commodities. And this correspondence actually is a Cartesian product of correspondences, and actually I will focus on this correspondence phi I, which is a correspondence that whose image of a given vector of prices is the solution of the consumer problem. That is, it is the arguments that maximize utility under the budget constraint. Okay, so we consider this correspondence. We show that this correspondence has a fixed point, and then we show that that fixed point is an equilibrium for the economy. So to prove that this correspondence has a fixed point, we use the Kakutani fixed point theorem. So this Kakutani fixed point theorem says that if we have a correspondence between us, defined on the set C, taking values in the same set, if this set C is non-empty, convex, and compact, if the correspondence is upper continuous, and if for each x, C of x is non-empty, convex, and compact, then this correspondence has a fixed point. So these are the conditions that guarantees that this correspondence has a fixed point. So actually, you have to prove that, in particular, this correspondence satisfies that conditions. And one of the conditions is that this correspondence has to be upper continuous. To get the upper continuous continuity of this function, actually, we use this second result, which is the Verge maximum theorem, which says basically that the argument maximum varies continuously when the restrictions, or when the set where we are looking for the arg maximum varies continuously. So one of the conditions that we need to apply this Verge maximum theorem is that this budget set correspondence has to be continuous. A correspondence is continuous if it is upper continuous and lower continuous. Yes.
5 minutes.
So very few. Okay, a correspondence is to prove upper continuity is easy. To prove lower continuity is not easy. We need that this correspondence has an interior point. Okay, and when we consider trading restrictions, this existence of an interior point may fail, and so this is the problem. Okay, so in this case, if we have trading constraints, we cannot consider as a compact set for prices, namely for the prices of the assets that are segmented. We cannot consider this compact set the simplex. So in this case, what we do is that we fix an exogenous compact set for that prices, and then we prove that at equilibrium, actually that prices will be bounded. And so this is what we have done. We look for conditions that will guarantee that at equilibrium, the prices of the segmented assets are actually bounded. So this is our point. So since I don't have many time, let me just focus on the following, okay? So this is our model. We introduce trading constraints. So trading constraints that can be price dependent. In this case, we cannot put the price of the segmented assets in the simplex. These are actually examples of trading constraints that the agents may face. And then what we were able to do was, first, we proved that for standard assumptions, this property, compensation of small losses in segmented markets, always holds. These assumptions mainly says that if we reduce the payoff of the segmented assets in the second period, we can compensate that increasing a little bit the consumption at date 0. This property allows us to prove that the price of the segmented assets are bounded by this ratio. If you are able to find an uniform bound for this ratio, then we are done. And actually that was what we have done. And to do that, we have to consider that we consider actually two cases. The first case is the assumption of essentiality of commodities. That assumption actually says that the utility of the endowments are strictly higher than the utility of any bundle that belongs to the frontier of the consumption set. So this is actually the assumption. With that assumption, we were able to prove that this ratio is actually uniformly bounded, because we were able to find an upper bound that was easy, but what is difficult is the lower bound, and we actually were able to prove that lower bound. Okay, the second case, just to finish. In the second case, so this is actually an example where that has equilibrium with the trading restrictions, but that the previous literature doesn't guarantee the existence of equilibrium for this example. So this is an example that now we can guarantee that there exists equilibrium. So the second assumption that we consider and that allows us also to prove the existence of equilibrium is the supermodularity of the utility function. Supermodularity, this is the definition, but if the utility function is twice differentiable, then this means that the second order cross derivatives are positive, and in economics the meaning of this is that the goods are complements. So if the goods are complements, we are also able to find an upper bound for the prices of the segmented assets. And for that, in that case, we use the Lagrangian function and the necessary Cantucker conditions. And using that necessary Cantucker conditions, actually, we were able to find an upper bound for that for the prices. And in this case, we have found this sum of ratios as an upper bound, and then using supermodularity, we are able to bound the numerator of this function, and by concavity, we are able to find a lower bound for the denominator. And
1 minute.
1 minute, okay. Actually, I think I'm done. So we find this upper bound for the prices, and then actually what we have done is to state new assumptions, because actually there is a huge literature on this topic when there are trading constraints, or for the existence of equilibrium when there are trading constraints. And actually what we have done is to add something to the literature, because we find new assumptions, actually this essentiality of commodities and supermodularity of the utility function as conditions, as new conditions that allows us to prove existence of equilibrium. And this way we enlarge actually the setting of economies where we can prove the existence of equilibrium when there is trading constraints. Okay, and I think I'm done.
Marta, I know the first three speakers have extremely hard task, which was to talk in 15 minutes. Okay, so I think you all did a very good job. And while we wait for questions from the audience, please write them in Q&A if you want me to speak for yourself, for you. I will actually ask Marta a minor issue, which is, where is credit?
Where is?
Credit.
Credit.
The title.
There is credit because agents can short sell the assets.
Okay.
Because I allow that the portfolio has negative coordinates, and negative coordinates means credit.
Yeah, short selling. Yeah, not
selling.
It depends a bit on how you do short selling and exactly how it goes.
No,
and
but
also, when you say the negative weights are short selling, or so my question is, do you include the risk-free asset? So one of the assets could be the
one of the assets can be the risk-free asset without any problem.
Okay, and then you are allowing for taking loans.
Yes, yes. But actually, in our models, to have credit, we don't need the risk-free asset, because we consider credit with any kind of asset that we consider.
Yeah, short sell.
So this is very general, I think.
Yeah. So anyone else who wants to pose Martha a question? I was just confused, Martha, because credit, for me, whenever you say credit, I think credit risk. It's a default, it's a problem of mine. But I think it was very interesting. And as I said, all the three speakers did an incredible task of speaking of such complex matters in 15 minutes or so. And I think it's really, really short. And I'm just happy that I'm not in your shoes. And I guess Torsten is also happy not to be in your shoes, because he will have more time. Okay, so it's now time to introduce Torsten Smith. He's been a co-author of mine for some time, or rather, we haven't published that much yet, but we have been working together for a while, and we both are interested in insurance and finance connections. And since I was the organizer of this session, I thought what he needs to be the main speaker, because the idea came from a project we both run, and so I decided on that matter that Torsten will be the main speaker. I hope the other three speakers understand. And I leave the floor to Torsten to speak more about the usage of affine models in insurance-related topics, which we do both think is very interesting. So Torsten, you do have more time. Actually, I think you have 40 minutes. I thought 30, but I think you do have 40. So enjoy and let us know what we are doing.
Okay, thank you very much, Raquel, for this kind introduction. And it's a pleasure to present here. I'm very happy to be in this kind of very diverse section where we can present such different aspects. And I also have had many questions to the previous speakers, but in let's say, for the sake of time, I did not pose too many questions. I will add a further view on finance, let's say, or financial applications and insurance applications from the aspect of fundamental valuation of prices. And I also will add a further class of stochastic processes, which are affine processes. And I think both could be interesting to the whole audience and also to the other speakers. This, what I present here is an ongoing project which has been started something like 5 years ago. It's joint work with Philipp Arzner, Karl Theodor Eisele, with Raquel. We have been working on the affine processes, and with Anne McKay and Moritz Ritter, because also at the end, I will bridge to recent machine learning deep hatching technologies. And so you can have a full view on this interesting field of finance and insurance in the realm of affine models. So the problem which started us, that was me and Ernst Eberlein, is that we have this low interest regime which puts big difficulties on insurance companies, because the contracts which they offer with, let's say, a very low interest are not attractive for policyholders. Let's say life insurance with small interest is not attractive. And therefore, this is a big problem, not only for insurance companies, but also for all of us, since we want to have attractive contracts where we can, let's say, in a safe way, invest with a good future return. And the question is, how can this be solved? And then Eckhard Platen gave a presentation in Freiburg, and I want to borrow from his literature on the benchmark portfolio, he has very long data series dating back, let's say 100, 120 or even longer on his benchmark portfolio. But today I present you something which is simpler, which is only the S&P 500. And here you see that over this time, this is really evolving. Of course, there are crisis times when this is going back. Here you have it on the log scale, but in comparison to, let's say, the interest rate risk is certainly safer on the safe side. But on the long horizon, even if you have World War II here, right, there is a clear outperformance of the S&P 500, and in terms of risk, you see that well, you earned much more money on the stock market here, and if you average the risk over a long time, then you are much on the safer side. So this encourages us a little bit to incorporate or to suggest to use stock markets as the main underlying for insurance products on a long time horizon. Of course, this poses a number of problems. Equilibria could be studied here, but then the setting gets very complicated. We have seen this in Marta's talk, that this is a very difficult question to answer. So I want to go a little bit more in the direction of fundamental theorems, and of course, hedging should be discussed. The risk which you get when you invest in the stock market, of course, in such a contract should be insured or kept in a certain sense. And the thing which I propose today is to incorporate guarantees in a kind of put type, so like from put options. And of course, I think there are also other more clever insurance-like ideas, but this is something for the future. Okay, such contracts exist, in fact, over, let's say, at least 40 years. They are a big market in the United States, and they are called variable annuities. You see here the numbers. This is really a very, very big market. And as mentioned, I want to provide a fundamental view on the valuation and then show you later on how this can be applied. So what is a variable annuity and what is the problem? So the variable annuity is something which is linked to your lifetime. So we have a stopping time, which is the lifetime tau. We have underlying index portfolio, could be the S&P 500 or whatever you choose. For simplicity, I normalize. And you have something like an option in an American option, American contract. You can cancel the contract, which is called surrender. So you have three types of benefits, three types of payoffs, which depend on how you behave. So if you did not die until the end and you did not surrender before, you get the guaranteed minimum accumulation benefit, which is the stock price, if the stock price is high, but it is at least the guarantee, right? The guarantee is either constant or it gives you an interest rate delta. So therefore, this contract can embed a guarantee. And if you think over 30 years, you look at the stock market, and I think it's quite attractive to give a good guarantee, a good deterministic rate here, which could be accepted. And here you see something which we know from financial markets. So you can decompose this as the guarantee plus a put option. And on the other side, you multiply this by quantities which are not traded, right? So this is an insurance-like quantity. Of course, my personal lifetime as policyholder is not even publicly available information. So this is not observable to the financial market. So here you have a non-traded wealth. And therefore, we enter the realm of non-traded wealth. And this is the first point which I want to make. Other benefits are easier or complicated, depend on how you look. So the surrender benefit arises at the time when you surrender. So at the stopping time, you say, I want to surrender my contract, then you have no guarantee. You get the value of the stock times a penalty, which is small in the beginning, but converges to 1 at the end. And you get also a death benefit. So if you die, you get an insurance, and here the guarantee is embedded. So you have to somehow study the valuation of these 3 parts, and all are linked to market quantities on the financial market and to insurance quantities. Okay, so for example, these kind of survival put could be a standard example of what you have to value. Of course, this valuation should be market consistent. So if a put price is available, somehow you need to take this information into account to come up with the value here. But on mortality, for example, you have a lot of historical data. This, of course, should also be taken into account. Then if you look in the literature, people say that tau is often independent of S. And now we had the corona pandemic where you saw, of course, stock markets crashed and mortality times go up. So, of course, this is true in standard situations. But in general, it's a little bit risky to underestimate dependence of mortality and stock prices here. It's very clear that for the surrender time, this depends on the stock market. If the stock market is very high, I'm more likely to surrender, which is very clear. Or if the stock market is very low and my stock portfolio is having low money, the guarantee comes into play. So I maybe want to exercise my guarantee, and then it's also more likely to surrender. So clearly the surrender time will depend on stock market. And therefore this needs a consistent model which models stock market and mortality, or maybe the stopping times in a general framework, and therefore I will use affine processes. Okay, what are the goals today? First, I show you a simple rule which mixes insurance pricing with risk neutral pricing, which can be applied to the valuation of this non-traded wealth. Then you will ask, okay, why do you do this? And I show you that there's a fundamental justification of this approach very shortly here. Then I go to a general affine framework for valuation, which is, I think, interesting per se. And you show that there are new difficulties arise, which are not present in classical valuation problems on financial markets. And I will, at the end, give recent results on deep hatching. So on the fundamental justification result and also on the affine framework, you find preliminary results in a working paper of us, which is on arXiv. And here the framework is updated and modified to ease the presentation a little bit. There's a lot of literature, and I will not comment this very thoroughly here. So the topic is around at least since quite a long time, and many people do different approaches to this. Indifference pricing maybe is something which is aside the framework which I look at today, but the others can be integrated. So valuation of non-traded wealth is somehow the question of having 2 filtrations and 2 measures, and how to mix them in a proper way. Ludger Rüschendorf from Freiburg with Plachki already did something in this regard in 1984, and Dybvig in 1992 applied this for the first time to financial markets for the valuation of non-traded wealth. And I just want to recap these issues in our notation. So the first observation is that you have 2 filtrations. So you have the financial market, publicly available information containing mortality tables, many information also on the statistical side, but you have private information on the insurance side. Private information contains my lifetime, my health status, and so on. So you certainly have 2 filtrations, F and G, and I will always use F as the smaller filtration, which is publicly available, and G as the larger filtration. We assume that the financial market is arbitrage free. This means on the smaller filtration, you have an equivalent martingale measure Q. in general, and this will not be my topic here, but it will be, it is one of the topics we discuss in the paper. We allow for arbitrage in the insurance filtration. So the insurance has more information, can do arbitrage on the financial market, but this complicates the matter a lot. Okay. In the case where you have this measure Q on the financial market and the measure P on the insurance information, we want to have a measure which I call Q dot P, which coincides with the risk neutral measure on the financial quantities, and conditional on the financial market, it behaves like P. So if we let the financial market run until the final time, all stock prices are available to us, conditional on this information, then the measure behaves like P. Okay, and this measure, QP, satisfies the following nice and easy rule. Computations under QP are done first by projecting to the financial market with the measure P. And then this is something which is FT measurable, like a European claim. Then you value this classically like a European contingent claim, taking the risk neutral pricing rule. Okay, so this is a very nice rule. And when Philipp Arzner and Karl Theodor Eisele brought this rule up, I asked the question, okay, why should we use such a rule? What is the justification? And it's very clear that the P expectation, P is the statistical measure, can be justified by taking a strong law of large number. So the insurance has a large portfolio, 10,000, 20,000 or more clients, which are in the same cohort. So they have something like conditional IID behavior, and then you average, and then you end up with this expectation under P. So if the cohort is large enough, this rule can be justified morally, but also more formally, which I want to show you now. Okay, so here comes our fundamental theorem. We have to introduce insurance markets and financial markets, and we will do so in discrete time to avoid technical difficulties. So you have the insurance filtration G, as already mentioned, an insurance contract. So think you're currently in time T, lifetime, everything's already discounted. So the maturity is the final time horizon where I will get my money. XTT is this amount of money, which is, let's say, adding the guaranteed minimum accumulation benefit, the death benefit, and the surrender benefit, and pushing everything to the final time by upcounting. And this is the payoff of the contract. So this specifies the insurance contract, which I buy by paying the premium at time T. Okay, if I come at tomorrow, T+1, this is a different contract because the quantity changed. So therefore we think at every time we have a new contract, which has this, is denoted by XTT. And then you buy this contract and hold it until the end. So this is a very constrained market. There's long only, so no short sales, no trading at all. So it's like infinite transaction cost. You buy at time T, and then there's no reselling. You hold this contract until capital T. You can, of course, surrender, but the insurance is obliged to pay you the final payoff. There's no trading and no hedging on this side, right? So it's a very market which is very different from the financial market. So the key to everything is the value of the insurance contract. So we do not say price because it's not so, it's not priced. It's more like an OTC contract. So the value is a GT measurable random variable PT. Okay. Now we will augment the current insurance information with the future financial information denoted by GTD, and then make the following assumptions. So this is the assumption on the insurance portfolio. These random variables, so you have not only one customer, you have infinitely many customers, X1, X2, X3, and so on. Like all our attendees here are in the in the insurance policy pool, and these contracts are GTT conditionally independent. So current state is taken into account GT, then you can condition in all the involvements on the financial market on publicly information, and conditional on these information, they are independent, right? So this is a quite weak concept, because we don't assume independence, only conditional independence. So they can be highly dependent, of course. They have the same conditional expectation, and they have existing second moments which also coincide, right? So this brings a conditional strong law of large numbers into play, which we will also play. So the insurance builds a portfolio, right? It's active, like in the Black-Scholes world, we have learned that the bank is not passive, the bank has to be active, there has to be trading, and here on the insurance side, it's the same. So the insurance forms an allocation. An allocation is given by finitely many non-negative random variables. So I assume that you don't need to buy one contract, you can buy many contracts, or you can buy fractions of a contract, but you cannot sell. So it's non-negative. And you can have only finitely many, right? So even if there are infinitely many portfolio holders, we will assume that an allocation is only with finitely many, and then we let n go to infinity and say, okay, it can be larger and larger. The value of the allocation, right, is you take the price times the sum over all psi k's, and the associated claim with the insurance has to guarantee and to pay at capital T is this kind of sum, right? So psi k times xk. While PT, of course, does not depend on k, we all have the same price. Xk depends on the individual, of course. Yeah. Accumulated P&L is given by this quantity, as we know from finance, classical way. And now here comes our strategy. The insurance is allowed to form larger and larger portfolios. That's a sequence of such allocations. And if the value of this sequence of allocations is greater or equal 0, but not 0, then we say it's an insurance arbitrage. So here comes the insurance arbitrage concept. Then we need a number of assumptions, uniform boundedness, convergence of the total mass, convergence of the total wealth, and we call this admissibility. And if there is no admissible insurance arbitrage, then we say there's no insurance arbitrage, right? So NIA for that. This is the insurance part. Now comes the financial part. This is classical. We have a finite number of discounted assets, which are denoted by S1 to SD. They are F adapted. We assume that there is an equivalent martingale measure in the F filtration. Here for the presentation, I make it a little bit simpler. I also assume that the insurance is not allowed to, cannot make arbitrage. So we will assume that there is an equivalent G martingale measure, right? Simplifies the setting a lot. The combined insurance finance value is given by the sum of gains from trading plus the sum of our value from the insurance allocation, right? So here we have a fixed psi, and then we have a fixed psi, and then we want to take limits in deep size, but we don't want to consider something like a large financial market. So on the financial side, this stays fixed, but on the insurance side, I can make a larger and larger portfolio. And I say there's an insurance finance arbitrage if this is greater or equal 0, but not 0, right? So here comes the tool. If there is an insurance finance arbitrage, we would say, okay, the prices are wrong. And if there's no insurance finance arbitrage, then we are happy. Okay, here comes the theorem. The theorem says, we have our assumptions, we have X, which are our claims, we have P, which is our price process, X, which is our stock market. If there exists an equivalent martingale measure with bounded density, yeah, on the G filtration, such that prices are dominated by expectations under the QP rule, right? Here's the QP rule with equivalent martingale measure Q, then there is no insurance finance arbitrage. This means if you use the QP rule, you're on the safe side, okay? What is different to the classical financial markets? In the classical financial markets, right, if you have something which dominates you, you have an upper bound, but the no arbitrage interval is an interval, you also have a lower bound. This you don't have here because there's no short selling. There's no reason why you can give this contract away for 0 and there's no insurance arbitrage, right? Because you just, this is obvious. So there will only be upper bounds for prices. We can enforce limits which say the price is not allowed to be too expensive because the insurance can make a risk-free gain if the price is higher than all such expectations. Yeah, so this needs a little bit more work. So the converse, there's no if and only if, right? So the converse is more complicated. If we have a time point such that this quantity is bounded from above and PT is greater or equal than the upper bound of all prices. So this is somehow like the upper bound of the no arbitrage interval. And we know if the no arbitrage interval is a singleton, right, a single value, then of course the upper bound is the only value, is arbitrage free. But if it's a real interval, then the upper bound is an arbitrage. So we also need to assume that PT is greater than the infimum, yeah. And then this says, okay, it's either the upper bound if this is a true interval, or it's above the upper bound if this is a singleton, then there is an insurance finance arbitrage. Yeah, okay, so this is the condition. And now for the following, we see that if we use the QP rule, then we are in the safe side. We can provide prices without insurance finance arbitrage and use linear pricing rules as follows. Now you might say all insurance valuation principles which I have been seen are non-linear rules, right? So why can we come up with a linear rule? And the reason for this is that we assume that the strong law of large number can be applied. So the insurance company, if she's clever, can get rid of the risk on the insurance side, right? You use the strong law of large numbers and there's no risk left on the insurance side in the sense that you can really reproduce these expectations. And if this is not the case, right, so if the insurance is not able to diversify completely, then you always have remaining risk here, and then you need to take the risk into account and you will end up with a nonlinear rule, right? So this is the first step, which assumes high diversification, and then you have a linear rule. If you're an insurance company, you also have to take care that you survive on a longer time. The regulator enforces you to add risk margins on top of this pricing rule. So the linear pricing rule is the first step, and on top comes some risk margin. Here you have an example, which is a little bit in the credit spirit, a doubly stochastic example. So assume that publicly information is encoded in the kind of stochastic process S, and the conditional probability of tau being greater t, so the survival probability, is a function of the full path. I denote this by ft s, so it can be fully path dependent, some function. And then if you apply the QP rule, this looks like this quantity. The P probability, right? This was exactly this thing, is a function of the path. And here you see you have something which is measurable with respect to the financial market. And then you use risk neutral pricing like in the classical sense. Yeah, so it's very easy, very useful for applications, and highly tractable. Okay. Yeah. The problem with general filtrations F and G is that you have a little tractability, and if you want to have more tractability, you need to use some tools like enlargements of filtration, and that's the next step which I want to show. We do it first with only one random time, which is the standard tool, and then I do it with more than one random time to have a little bit of generality. So the difference to the classical enlargement of filtration is that we not only have two filtrations, but we also have two measures. Okay. So you have your random time Tor, and you assume that the Tor is an atom in this kind of probabilities. Means when you condition on Tor greater than T, then you can go to the smaller filtration. This is the typical assumption which is satisfied. It's called sometimes the H condition. It's satisfied for doubly stochastic models. And if you have this probability, then you can use the Azema super martingale here now under the QP rule to compute expectation of, let's say, a payment stream. A is an G adapted process. You get at Tor the value A Tor. That's exactly what we need for the surrender benefit and for the death benefit. QP rule says, well, of course, if Tor already appeared, this is A Tor, but otherwise you can use this kind of QP expectation and have to multiply it by GT to the -1. And this is the pricing rule which you have. Okay, that's not so surprising. Here I show you that if you have something like cumulated intensity capital lambda T, which is F adapted, you have kind of this doubly stochastic assumption, then you know GT exactly looks like e to the minus lambda T, right? So there's no Q averaging, only P averaging here. That's very nice and useful. And then you end up with a formula which looks like this. You sum over all times Tor equal S, then you have S AS if Tor equal S, and then you must multiply by the probability that Tor is equal S, which is of this quantity. And this is how you value such payment streams, right? So this gives you, in a simpler example, the right rule for the valuation. Now, we have two stopping times. Can we also do it with N? Two stopping times, you need the atoms Tor greater than T, sigma greater than T, Tor greater T, sigma smaller than T, sigma greater than T, Tor smaller than T. So you need many such atoms. Therefore, for two stopping time, it's not sufficient only to look at two, you need to look at more, right? Which I will show you also in a second. So we have many of these atoms. So N of these atoms. We have our Azema super martingale for the atom I, which is denoted by GTI. And then we are working on the omega T, which is spanned by these atoms, right? So on this omega T, the expectation is given in a similar way like we have seen it previously. You need here this condition, then you can use GT to the -1, and you have again the QP expectation of A indicator on PTI. So it's the same rule in a little bit more general perspective. Proof is essentially the same. Okay, now if you have our two stopping times, Tor1 and Tor2, you have such an, you have such an intensity. Tor is the first time where the intensity crosses an exponential barrier. You have two exponential random variables which have a continuous copula, right? Then you have a quite general setting which well, accommodates all models for mortality which I have ever seen, I would say. And then you can compute these kind of survival probabilities, let's say the Azema super martingale with this copula, right? So this is very flexible and you can do whatever you want with this kind of approach. Now, here are the atoms, Tor1 greater T, Tor2 greater T, Tor1 greater T, Tor2 equal to I, but smaller than T, and the, everything what you want to have, right? Because you need to check, is the surrender benefit at this time, is survival benefit at this time, and you need all these kind of quantities, okay? So please memorize all these formulas. You see, well, you can compute everything, and indeed, you can price, let's say, a surrender benefit or death benefit with the similar formulas. Yeah, okay. So I hope I persuaded you up to now that enlargements of filtration can be applied here in this general framework. And now it's time for an affine framework. If you look to the literature, there are many works on affine processes, on mortality. There are many works on affine processes for stock markets, Heston models, whatever. But I have not found a single paper which is able to connect both markets. And as you have seen, of course, you need to connect mortality, surrender intensity, and stock market. And I show you how you can do this. So here is a process Z is a process in discrete time, which is simply called affine if it has this structure. Maybe you want to realize that this is quite different from the classical affine process like studied by Duffy, Filipovic, and Schachermayer, which are assumed to be Ito semi-martingales. Such semi-martingales are stochastically continuous, so they will never jump at a discrete time. Affine process in discrete time jump only at predictable time, so they have a quiet structure, which we started in a paper with Martin Keller-Ressel and Robert Wardenko. You have a little bit more freedom in discrete time to model than in these kind of stochastically continuous time models, which can be exploited here. Okay, stock price depend in an exponential affine way on the affine process. The intensity, let's say only for mortality here, depends in an affine way on the affine process. Of course, lambda t must be an increasing process, right? So you must choose B such that these components are increasing. And now you may wonder, well, if Z is like Coxinger's or Ross, how do I get an increasing process by integration, right? So if you have a Coxinger-Ross process, which is non-negative, you integrate this. You do also in the classical case, and you take the two-dimensional process, which is the integral and the Coxinger-Ross process, and then B just charges weight on the integral and therefore is increasing. Yeah, so this is the classical way, but you still have to work to get an increasing process here. Then we do the progressive enlargement of the filtration F, which is the Z filtration with tau, and then we can apply our previous formulas. In the PQ rule, we need P pricing and we need Q pricing, right? So we assume that there exists an equivalent martingale measure where our process is again a martingale. Yeah, and again, an affine process. So this is the Q representation of our affine process, right? Okay. You could make this more complicated if you want to, but then you possibly also get into trouble. But this is an assumption, right? So we choose an affine equivalent martingale measure. And now we need to do a kind of small trick. We have seen that you have all these conditions, and now if you take expectations of the affine process, you have to iteratively proceed through times. Expectation of the affine quantity is again exponential affine, then you can do this again and again, and by this you get such iterations like you find here, right? So alpha q depends on the aq, which is this coefficient, and the beta q from the next period. So you may believe me that this is possible, but this is already complicated. You have to iterate through all times. And something like S tau, the death benefit, is decomposed in the sum over all SS's, where tau is equal to S. And now these quantities can be valued, these quantities can be valued, and then we end up with the first valuation formula, which looks like this. And here you see all these kind of coefficients which are obtained by iterating, and then you have to sum these up. You might notice that ZT is not iterated, right? So this is the sum over the alpha q's, and for the Z we always take conditional expectation when we only have the beta q t plus 1 here, right? Okay. Now, of course, we need 2 times surrender and survival times. You have 2 times this end intensity, and formulas get more complicated, but morally you see, okay, this also can be done. So this was the Affine framework, and to make it also sexy at the end, I want to show you some recent deep hedging results. So you might wonder the question, if you look at this nice work from Hans Bühler, Lukas Gonon, Josef Teichmann, and Ben Wood on deep hedging, can this be applied here? And the answer is yes, but it's substantially more complicated. And I think the fundamental approach, which we have been shown in the beginning of the talk, shows that if you want to hedge as an insurance company, you want to build your portfolio. So you have to decide how many insurers have. So you choose a number of N of insurers, and then you compute the prices, which are, let's say, of this survivor call. And here you have for each insurer the TOR I. And then, let's say you average, take 1/n, and you look what is the outcome of the portfolio. So this is, of course, much more complicated and much more noisy than if you simply look at a call. And this also turned out to be the case in our experiments. So if you think a little bit, you would think, okay, for hedging, I would use the delta here, and here maybe I replace the indicator by the probability. And if this is something like 60% to make the results very visible, that you see the difference, you would expect something like 60% times the delta in the hedge. And this is exactly what we also found. So how do you apply deep hedging? Deep hedging means you parameterize this. Sorry? 3 minutes. I make it. You parameterize the delta. You assume that this is a Markovian hedging strategy. So this depends only on time and on the stock price. You parameterize this delta by a neural network. And for us, it's sufficient to have something like 50 neurons and 2 layers. Works very well. And then you compute your hedging on simulated data. So you choose parameters, Black-Scholes with a certain parameter mu, certain parameter sigma, and you choose the exponential intensity, and then you simulate, and then you train over, let's say, 100,000, or I have even 200,000 simulations. And then you fix you try to adjust the weights in this neural network so that the square deviation of the hedging error is minimal. Yeah, okay, so this is our approach. Here you see the outcome, the orange line with the dots are the strikes which I implement. So I have many strikes for which I try to fix my delta, and the orange line is the learned delta, and the blue line is the theoretical delta. You see it goes only up to 0.6 and not to 1 like in the standard delta, because it's multiplied by the intensity. And here you see the learning curve. So it actually in the beginning goes fast, then it takes quite a long time. So we have over 200,000 simulations here, or steps here, where each step has 500 simulations in it. So that's quite a road which you have to go. And this is much more difficult than in the case where you have no insurance question. Okay, let's conclude a little bit. The integrated view gives you, I think, a better view on what is the insurance strategy, what is the finance strategy. We have had the QP rule, which shows how to make nice values. We have the Affine framework, you have hedging strategies, and all which you have seen here. I want to use also a small advertising. I edit a special issue on machine learning in finance, insurance, and risk management. And if you're interested, you find the link on my homepage or on the risks page. You can still submit papers there. I would be very happy if you do so. And now I have to close. My time is over. Many thanks for your attention. I look forward to nice questions. Here you find also literature, and thank you very much.
Thank you. Just on time, of course. And while we wait for any Q&A, the audience has not been very eager in asking us many things, but it might be this time. Does any of the other speakers want to pose Torsten a question? No? No. So could you just, it's a bit ridiculous because I'm joined with you in some of the projects, but could you just explain why the discrete time setup is, where is the problem using continuous time?
Can you repeat, please?
Just a bit more elaboration, maybe to clarify. So you choose a discrete time setup, right?
Yeah.
What is the problem with using a continuous time? Where does it get stuck?
I think we are not yet there to go to the continuous time. We still have a lot of difficulties in the discrete time setting, but per se there is not there's not a difficulty, right? So the first difficulty would be then you say now you have at every continuous time. On the insurance side, I think discrete time is actually very sensible, right? So insurance contracts, well, you don't trade them any day, so it's very natural to have discrete time. If you surrender in the insurance contract, right? So this thing here, the stopping time, often you are not getting the money at the time where you surrender, but at the end of the quarter, right? And also the payoff is not at TOR itself, but it's at the end of the quarter. So actually it's very natural and the right setting to have a discrete time setting on the insurance side. And of course, you could replace simply the kind of financial market with a continuous time financial market. But then we thought it's a little bit disturbing to mix these kind of time things. So here we wanted to do it technically as simple as possible. And you already run into enough difficulties, right? So the fundamental theorem, like I showed you, is still not in the form where I would say we have understood completely what is going on. We have no if and only if conditions. And so I think there are many other problems which we solve first before we go to the continuous time.
Okay, thank you. I think there is no questions, and I
have one.
Okay, so go ahead.
Well, possibly two, depends on the answer of the first. Can you explain again why you don't allow short or the reselling of the contract?
Because this is not natural, right? So you could also say there's a secondary market where you can trade, but in general, you have your life insurance and there's no liquid market for this, right? If you want to sell this, maybe you have to find a customer, your health conditions changed, so many things are very problematic. What would we achieve by this? We would be able maybe to come up with a lower bound. So what would be a minimum price bound? And this is, I think, less interesting, right? So take the QP rule, and then you have at least an upper bound. Coming up with a lower bound was not so much our intention. So we wanted to clarify, when is the insurance able to make a profit, right? So when is the price actually too high in the limit where the insurance can get rid of any risk, and therefore the upper bound is this kind of risk. And the reselling would be not by the insurance anyhow, it would be by the policyholder. Then you could clarify, is it, if the price is very cheap, so what happens then, right? So what can you somehow profit from this, because you have this kind of very cheap contract which is too cheap, and then you can sell it on the market. I think that it's maybe an interesting mathematical question, but from the economic viewpoint, a bit less.
I was really thinking about the precursor to the housing crisis in the US, where most of these the mortgages were rebundled, and so you had it was not the contract itself that was sold, but they would pool a large collection of contracts, and it was these that would be sold. So I was thinking in that way.
Well, as far as I know, in insurance, we are not there yet in terms of.
It's a good point. It's a good example on the housing right that you can sell it there.
Okay. Are there any more questions? If not, I will ask Torsten to stop sharing so we can take a nice picture of us. So now smile, all of us. Are you ready? No, not ready? Tira os óculos? Yes. Okay, all ready? Okay, thank you very much for the attendees and for the speakers for having accepted to participate in this session. It was a pleasure to me to see you virtually, but still to see you. And I hope we can go ahead with our studies and further discuss our works in the future. Okay, so now I applaud all the speakers. I'm the only non-speaker. You can applaud each other. And well, to the audience and also to you, now we can go to the other sessions. Okay, now we have the lunch break and then the conference goes on. Okay, it was a pleasure to coordinate this session on the 80th anniversary of the Portuguese Mathematical Society. And see you soon somewhere. Okay, thank you.
Bye-bye.
Bye-bye. So,
Bye. Thank you.
thanks, bye.